All right, everyone. So we're going to start out with filling in these. I'm going to use the auto filled in one already. So all we have to do is just kind of read along here. You're going to fill them into your spots where you have them. So a rational function is a function that can be written as f of x equals p of x over q of x. It's because the word rational, we should be thinking of a fraction, right? So it's any function that can be written as a function, fraction, sorry, where p of x and q of x are polynomial functions, and q of x is not equal to 0, because if q of x was equal to 0, then this would be undefined, all right? So now, we look down here, vertical asymptotes. Let me scroll down a little bit. All right. All the vertical asymptotes. A rational function f of x is equal to this. Has a point of discontinuity for each real 0 of q of x. What does a point of discontinuity mean? Well, a point of discontinuity is anywhere the graph has a gap or a break or a hole. All of those fall in there. Okay, anywhere that has a gap, a break, a hole, a jump you may hear, because it'll look something like this, where the graph goes and then it stops and it starts back up somewhere else. All right, all of those, they're all gaps, breaks, holes, jumps, all those that are different types of discontinuity, all right? So it's for each real 0 of q of x. So yes, that means that we have to find the zeros for some of these functions. So if p of x and q of x have no common real zeros, then the graph of f of x has a vertical asymptote at each real 0 of q of x. So that just means wherever, if they're not in common, that means that each real 0 of q of x is going to be a vertical asymptote. Vertical asymptote, yet again, is our vertical dotted line where our line and our graph cannot cross. All right, if p and q have a common real 0a, then there is a hole in the graph or a vertical asymptote at x equals a. So a good example of this is if you have something like this. X minus 1 over x minus 1. All right, when we do this, x minus 1 and x minus 1 will cancel, typically, right? So if those cancel, we're just left with, this is y equals x. Y equals x looks like this. That's nice and easy graph to draw, okay? So y equals x is easy. The problem is there's an x minus 1 here and an x minus 1 there. So we have to account for that because x cannot be equal to 1. At x equals 1, we should be, according to our original function, discontinuous. There should be a hole there, all right? So this is going to be our hole. So at x, when we've got it set up here, we're going to draw our graph, but at x equals 1, I kind of want to put a little gap there because there shouldn't be a point right there. It should be open because that is a discontinuous spot. All right, so that's discontinuous. All right, scrolling down here, vertical asymptote, or horizontal asymptotes, sorry. The graph of a rational function has at most one horizontal asymptote, all right, 1. The graph of a rational function has a horizontal asymptote at y equals 0 if the degree of the denominator is greater than the degree of the numerator. So, degree of the denominator, that's greater than the degree of the numerator, then the asymptote is at y equals 0. And again, that's because if we remember our function, we remember our graph for y equals 1 over x. Here, the degree is bigger on the denominator than it is in the numerator. There, we always had our asymptote at y equals 0. So it's very similar here, just carrying over for any time that the degree in the denominator is bigger than the degree in the numerator. All right, if the degrees of the numerator and the denominator are equal, Okay, so this time the degree of the denominator is equal to the degree of the numerator. All right, then the graph has a horizontal asymptote at y equals a over b. So y equals a over b. A is talking about the coefficient of the term of the highest degree for the numerator. Okay, so it's a coefficient from the numerator. B, that's all A. B, we'll use circles. B is the coefficient of the highest degree from the denominator. So in other words, your leading term. As long as we're in standard form, it should be our leading term. So our leading term coefficient in the numerator over the leading term coefficient in the denominator. All right, whatever that may be. To give you an example for that one, it would be y equals, let's say, 2x minus 1 over 3x plus 1. All right. For this, our degrees are the same. So that means that it follows this one true. So then we have to go to a over b. A just so happens to be 2. B is 3, so it's y equals 2/3. That would be our horizontal asymptote. All right. And looking at the last one, if the degree of the numerator is greater than the degree of the denominator, then the graph has no horizontal asymptote. So here, degree of the numerator this time greater than the degree of the denominator. Then there's no asymptotes. All right. All right. That's part 1 of the notes. Please check back to see part 2 in a second.